Welcome back to Autonomous Mobile Robots. I am Margarita Chli, and in this segment, we're going to look into place recognition. So we're going to start at looking at a problem which is akin to place recognition, namely object recognition. So the question is this book present in this scene? So what do? We extract some features, for example, sift in this case, and then try and match them. Now, since there are a lot of corresponding matches between the book and this scene, we can say with some certainty that this book is present in this scene. So, using this principle, we can definitely find an object in an image, but can we find one object in multiple images? And then how about finding multiple objects in multiple images? Extending this to scene and place recognition, the questions we are looking at are, is this image in my database? Or from the robot's perspective, have I been to this place before? Which is essentially what we term as the look closure problem or the kidnapped robot problem. In order to do this, we're going to use some analogies from text retrieval. So in the same way that Google does it for documents, we're going to look at visual words. We're going to look at what we mean by a vocabulary of visual words and essentially the bag of words approach. So let's look at how we build a visual vocabulary and what it actually means. So we take our image collection of training images, which is what we have here, and then what do we do with them? In the same sense that we've done with the book before, we extract some features. Sift, surf, or your favorite feature type. Then from these features, we take their descriptors and map them into the descriptor space. In this descriptor space, we perform some clustering to form what we call visual words. So essentially, visual words are clusters of descriptors that have appeared in my training set. So let's look at what some of these words look like. So using these visual words, we can now describe a scene as a collection of words, an image as a collection of words. And then looking at those words in the database, we can find out which images contain a similar collection of words. But what if we need to find an object or a scene in millions of images or even more? Then you can see that this is a scalability issue. And we're going to tackle this by building a vocabulary tree out of them and using the inverted file system, which is a way of efficient indexing in the tree. Let's look at how we can build the vocabulary tree. So first of all, we need some training images from where we extract some features and then map them into descriptor space. So here's an image, here's another image. In this case, sift features are used. And then so on and so forth. We populate the descriptor space with all the features that have appeared in the training images. Now, in order to start clustering, start creating clusters in this descriptor space, we proceed by hierarchically partitioning this big space into smaller clusters via k-means clustering, for example. And then you could see how this structure then forms what we call the vocabulary tree. So starting by smaller cluster of descriptors to bigger cluster of descriptors. Now, in order to populate this tree, we take some model images and we extract features from an image like this. So we let this feature pass down the tree one by one and attach a label or a copy of this image at the end of every node. We do the same for multiple images. And this is how we populate this vocabulary tree little by little. So all of this is going to make sense when we start looking at what happens at runtime when we have a test image. So with a test image, in a similar way as we do the training images, we extract features. So we extract the first feature and we let it go down the tree. And you can see that according to the feature that we've just extracted from the test image, these two images are more likely to correspond to the test image. Now, if we do this for the next feature and the next feature, then you can see how gradually those probabilities start evolving. And in this simplified example, we just used 3 features, and obviously this is the highest probability, and hence this is the image that we're saying that corresponds more likely to my test image. So this test image corresponds to this image from the database that we have. Now, to make the search for images more efficient, we use the inverted file index. So the inverted file database looks a bit like this. So we are stacking all visual words that we have ever seen in the training phase, and then along with every word, we link every word to the list of images that it appears in. So what happens is that at the query image, when we extract features and map them into words, we can get this set of visual words that appear in image Q. And then this particular word, 182, then can vote directly for these 3 images where it has appeared before. And in this way, we can see how each word in the training image Q can vote directly for an image in the training database. Now, some words are more important than others, and like it is the case in text retrieval. And for that reason, we use the term frequency, inverse document frequency, to weigh different parts of the voting array with a different weight. So the term frequency is essentially the frequency of this particular word in this image over all the words that have been observed in this image. And then the inverse document frequency is formed as the logarithm of the number of all of the documents, or images in this case, over the number of all of the images containing this particular word, WI. The term frequency, inverse document frequency of this image is then the product of these 2 values. And this is then used as the weight of each word in the voting array in order to weigh down the importance of common words, like these ones here in text retrieval, and give more weight in more distinctive words that appear in the image. Probably the best performing pipeline for place recognition is FabMap by Cummins and Newman. So what they do is they use training images to build a bag of words database. And then they also use a probabilistic model of the world where they say that the world is a set of discrete places. Now, each place is essentially a vector that encodes the occurrences of visual words in the local scene. What you see here is some examples of this method in action. And these probabilities here denote the probabilities that the images on the top and the bottom row come from the same place. So as common scene structure is being suppressed, images like this, which capture a lot of common image structure, don't score very well in the probability of coming from the same location. That means that we're not entirely sure that this wall is exactly the same as this wall. However, in more distinctive places like this one here, we have enough distinctive features to say with high certainty that this image comes from this location, despite the fact that the worker is no longer there. So FabMap uses a Chowley tree in order to capture the dependencies of these words to distinguish the most characteristic structure in the scene. And this is what is giving it a very high performance. Also, it's important to note that their binaries are available online. Now, the visual vocabulary holds only appearance information. That means it discards any spatial relationships between the features themselves. So when this is the case, it means that two images that have the same features but only shuffled around in the image, they would be 100% match when we use only appearance information. Now, if we expect different arrangements of the same features, then one might use geometric verification. For example, ransack, where the k most similar images are fed into a geometric consistency test. Here I denote for you some interesting papers for further reading, and with this we conclude this segment on place recognition.